Molecular compounds followed by acids, a chemical family. Let's begin by talking about binary molecular compounds. While I'm familiar with this term binary, binary clearly means that there are two elements in a compound. And I know every time a binary compound is written, it will end with the ending IDE. What makes it a molecular compound is that we have groups of nonmetals sharing electrons, creating a molecular compound. Binary are two elements. Binary ionic, they show us a metal to a nonmetal. Binary molecular show us nonmetal to nonmetal. So the very category of elements create an ionic or a molecular compound. We wrote this note once on our periodic table just to remind ourselves it was the test-taking tool. If it's not on your periodic table, it might be a very good idea to remind yourself of these definitions. If I have a metal to a nonmetal, I hook by charges. And that's the whole game we've been playing so far in our journey. Ionic compounds are built of ions, something from the left compared to something to the right, a positive to a negative, a cation to an anion. We check to see if they need Roman numerals in their names for those transition metals. Today's next step, the world of molecular compounds, a nonmetal hooked to a nonmetal. Molecular compounds use prefixes in their names. We do not use prefixes for ionic compounds. We do use prefixes in molecular compounds. That is the next step today, nonmetals hooking together, so just items from the right-hand side of our periodic table, an N hooked to an O, a C hooked to an S, using prefixes to let us know how many of each there are. Binary compounds come in two categories, ionic or molecular. Binary ionic, metal to nonmetal. Binary molecular, nonmetal hooked to nonmetals. Since they form from different elements, we have a different set of rules for naming them. When we name molecular compounds, we use prefixes. The prefixes we use tell us how many of each atom there are in our formula. For instance, if I wanted to let you know I had just one atom, I would use the prefix 1 to represent the subscript 1. I would use the prefix di to represent the number 2 if that were my subscript. Tri is the number for the subscript 3. Tetra is for 4, and penta is the number 5. Mono, di, tri, tetra, penta for the subscripts 1, 2, 3, 4, 5 respectively. The subscript 6 gets a prefix hexa. 7 is the prefix hepta. Octa for the number 8. Nona for the number 9. And deca for the number 10. Counting chemistry style. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. When we name binary molecular compounds, remember, two nonmetals hooked together, two nonmetals make a molecular compound. The rules for naming these compounds are quite simple. We simply say the name of the first element. We say the name of the second element, but it ends in IDE. The last name will end in IDE. And we put the appropriate prefix to indicate how many of each element there are in our chemical formula, using the prefixes we just wrote together to indicate how many of each atom we are. If the prefix for the first element in our binary molecular compound is a 1, if the prefix is a number 1, it may be dropped. I don't have to say mono for the first element. Mono may be dropped for the first element only. but it must be said for the second element. I may drop it for the first, but it has to be there for the second element. A good example of what I'm saying. Let's name this molecular compound CO. C stands for carbon. O stands for oxide. Putting on the prefixes, notice it's just the last name that ends with "ide." The name of the first element, say it just as it is. The name of the last element must end in "ide." So far, we say the name of the first element, say the name of the second element, ending in "ide." And now we're told, put on the appropriate prefix to indicate how many of each there are in the formula. One carbon, we would say monocarbon, and one oxide, monooxide. What my suggestion is, if the first element is a 1, as in this example, you may leave off the mono from the first name. So instead of saying monocarbon, we can simplify to just say carbon. But if the last one is also a 1, it must be there. This correctly named is monooxide, but we'll lop off the double vowel problem and just simply say monoxide. CO, carbon monoxide. Do not reduce the subscripts as we did for binary ionic compounds. Binary ionic compounds must be in the lowest ratio possible. Binary moleculars, leave them alone. Let's practice. We're going to say the names of these binary molecular compounds, just saying their names. The formula of N2O. Notice N is a nonmetal, O is a nonmetal, categorizing this binary molecular compound. We simply say the name of the first element, nitrogen, say the name of the second element, ending in "ide," oxide, and put on the appropriate prefix. The prefix for 2 is di, so the first name dinitrogen. The prefix for the number 1, that subscript 1, it's not written but we know it's there, is mono. And instead of saying monooxide, we lop off the double vowel to simplify it, monoxide. We've just written a formula, N2O, and named it dinitrogen monoxide. PCl3. Notice the first element is just the number 1, so I'm going to choose not to say mono and just simply write its name, phosphorus. Cl, ending in ide, is chloride, and the prefix for the number 3 is tri, trichloride. Pause the video right now and name the rest of these compounds, and when you're ready to check your work, start it up again. Don't cheat yourself of the lesson. Pause the video, work ahead of me, then turn it back on when you're ready to check. All right, welcome back. I bet for letter C, you wrote sulfur, hexa for number 6, hexafluoride, sulfur hexafluoride. Letter D, just one oxygen, so I'm going to leave the mono off, oxygen, difluoride. Cl2O8, the prefix di, chlorine, oxide. Lopping off the double vowel sound, dichlorine, octoxide. And your letter F, sulfur trioxide. Notice it's only the last name that ends with ide. We say the name of the first element just as it is. The last name ends with ide, and we place the appropriate prefix onto the elements to tell us how many of each there are. Work ahead of me right now, pausing the video, and turn these names into formulas. When you've got them down, turn it back on and check your work. Letter A says nitrogen trifluoride. Nitrogen symbol is N. The symbol for fluoride is F, and to let you know there's 3 of them, we simply write NF3, nitrogen trifluoride. Disulfur dichloride. Disulfur dichloride. S2Cl2. Dinitrogen tetraoxide. Dinitrogen tetroxide. N2O4. Octoxygen dichloride. Oops, there's a typo there. That's an IDE ending. Octoxygen, that's 8 oxygens. Dichloride, Cl2. O8, Cl2. Trinitrogen pentoxide. Trinitrogen pentaoxide. N3O5. Binary compounds end with "ide." Only the last name end with "ide." Remember, binary compounds can be ionic, no prefixes, or they can be molecular, yes prefixes. Ionic compounds are built of charges. Ionic compounds, we take a positive and negative and crisscross. Molecular compounds are neutral. There are no such thing as charges, so we must use prefixes in the name to tell the reader how many of each there are. Learning to count chemistry style. Let's say them again just to remember them so they begin to stick in our head. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Friends, the last thing that I'd like you to do is to take these prefixes and find a spot on your periodic table so that come test day, you've got them handy and don't have to worry about forgetting. A test-taking tool, learn to count chemistry style. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Complete your periodic table test-taking tool area wherever you have a spot. And when you're ready, start up the next video on the lessons for acids. Welcome to our lesson on naming acids. Acids are a chemical family that are very unique in the sense that they have characteristics in terms of pH that are unique. They have bitter and sour tastes that are unique. So they are a special class of chemical family, and they're the opposite of bases. Perhaps you might have heard of acid and base chemistry, ranking the strength of the acid and a base on something called a pH scale. Because they are a unique set of chemicals, a family of chemicals, we have a unique way of naming them. Acids are a chemical family, and I'm writing that down. Acids are a chemical family that, and I'll put a comma, when dissolved in water, ionize to release hydrogen ions. Let me repeat that back as you're writing it with me. Acids, which are the opposite of bases, they are a special chemical family that when I dissolve them in water, making an aqueous solution, they ionize, and when they do so, they release hydrogen ions. Acids are hydrogen ion releasers. Acids are formulas that start with H. Acids, when we look at their formula, we're going to recognize those as their chemical formulas. Acids have chemical formulas that always start with hydrogen. So H plus will always be their first name, and that's how we recognize acids in terms of a chemical family. If they start with an H, hydrogen ion is the acid ion. Acids taste sour. Think of like citric acid in lemon juice, or citric acid that might be in vinegar even. Acetic acid is in ketchup. They have that sour taste. They have pHs that are lower than 7 on a pH scale. They are the opposite of bases in terms of a chemical family. We have a whole chapter devoted, much later in our journey of chemistry, but a whole chapter devoted to acid-base chemistry. The purpose of talking about acids in this particular part of our chemistry class is to learn how to name them. Acids have chemical formulas that start with H+. That's the hydrogen ion. When we name acids, whatever the hydrogen ion, the first name, hydrogen, whatever it hooks to for the negative ion determines how we name it. Let me clearly put this in terms of a chart, and because I wrote kind of large in this area for your benefit to see what I'm writing, you can definitely fit what I'm about to write in this area of your notepad. But I'm going to just put a fresh piece of paper up so I can write it out large, and you can very clearly then copy it with ease into your notepad on page 12. So the name of my chart, I'm going to call it Naming Acids. When I'm naming acids, this little chart or grid is going to help me in predicting the correct way to name acids. In a first column of our chart, let's put in the original ending. Original ending, column 1. In our second column, let's write that out as the acid name. And then we'll write in a third column, example. Alrighty? Just creating, and again, you can squeeze this into the notepad. I'm overemphasizing making it quite large. Sometimes we have ions for last names, and remember the original ending, this is what the negative ion, because the first name is always hydrogen. Hydrogen hooked to some element. Let's call that some element X. X could be a binary compound, it could be a ternary compound. We have binary acids and we have ternary acids. And whatever that hydrogen hooks to, if it starts with an H, it's an acid, and whatever it hooks to will determine how we name it. Let's suppose we have an original ending IDE. Now let me show where those come from. I'd come from these monoatomic ions on the front of our periodic table. Fluoride, F-1, chloride, Cl-1, bromide, Br-1, oxide, sulfide, nitride. Hear how if they are monoatomic negative ions, they end with IDE. Sometimes the original ending is "ide." If that's the case, if the original negative ion ended with "ide," here's now how to name them in an acid rule. We say hydro, and then whatever that root word is for the element ended with "ic," acid. Hydro, root word, acid. Let me give an example to help clarify. Acids always start with hydrogen ion, H with a +1 charge. If it starts with an H, it's now considered an acid. Acids release hydrogen ions. They'd have a pH below 7. For our sake, anything that starts with an H we'll recognize as an acid. This special class of chemical family has a unique way we name it. Let's take this H and hook it to something over on this side that would end in "ide." Let's just pick chloride, Cl with a -1 charge. So the formula HCl, +1 balances a -1. This formula starts with an H. We would have named this hydrogen chloride. Here the IDE ending. Old school way, hydrogen chloride, naming a binary compound. But now say it as an acid with me. In terms of writing it as an acid, we have hydro, root word, ic. That root word is coming from the negative ion. Hydrochloric acid. Let's write that in. HCl is an example. Hydrochloric acid. If the original ending were IDE, hydro, root word ic, hydrochloric, HCl, hydrofluoric, HF, hydrobromic, HBr, hydroiodic, HI, hydrosulfuric, H2S, balancing charge, and so forth. Hydro, root word ic. Sometimes the original endings end with ITE. If the original ending ended with ite, we know it had to come from a polyatomic ion. Let's find an example from our polyatomic ion chart that ends with ite. Here's one, nitrite. Here's one, sulfite, phosphite, sulfite, chlorite. There are many examples that we're seeing of polyatomic ions that end with ITE. So let's just take ite as an example. The rule says to name now as an acid, we go straight to the root word and turn the ite to us, acid. Notice, very important, there is no prefix hydro. Hydro is only heard when the original ending were IDE. If the original ending were an ite, it came from a polyatomic ion, didn't it? An ite turns to us. Let's model. Let's just grab the first one I had said earlier. Nitrite, NO2 carrying a -1 charge. Acids always start with a hydrogen. NO2 is a polyatomic ion. NO2 -1 is called nitrite. Now, we would have named this hydrogen nitrite. We would have named it hydrogen nitrite, but now let's name it correctly as an acid. Acids start with H. The H is not heard in this name, however. We go directly to the root word, ite turns to us, and say it, we get nitrous acid. Nitrous acid. Now I know it starts with H because the name acid tells me that. Hydro is only heard in those binary acids that ended with "ide." We do not hear hydro in this word. It's simply nitrous acid. Hydrogen nitrite became nitrous acid. There's one more ending we hear on polyatomic ions quite often. It's the ATE. Acetate, nitrate, permanganate, chlorate, sulfate, phosphate. Hear the ATEs? Sometimes the endings of negative ions end in ATE. Now, to name some negative ion correctly as an acid, do not say hydro. Ate simply turns to ic, and we get acid. Ate turns to ic. Let's model that. Let's hear just the first one I might have said. NO3 -1 is called nitrate. Now, hydrogen always is the first name for an acid. An acid is a hydrogen ion releaser. If I see a formula that starts with an H, I know it's an acid. Let's hook it to a polyatomic ion, NO3, who carries a -1 charge. We would have named this compound hydrogen nitrate. But now correctly as an acid, do not say hydro. We simply go to the root word ic. This simply gets named nitric acid. If the compound ended with ide, I-D-E, hydro, root word ic. If the compound ended with ite turns to us, and we get chlorus, nitrous. Sulfurous acids would be an example. Ite turns to us. And if a compound originally ended with ate turns to ic, and we had an example, nitric acid, sulfuric acid, carbonic acid, phosphoric acid. Here I'm going directly to the root word and ending it with ic. We don't need to say hydro because we said the last name acid, and we know acids always start with hydrogens. These binary acids who had original endings ide is the only time I hear hydro. That's so important. The only time I hear hydro, only time, is if the original ending were IDE. Let's turn our page in the note pack that we've talked through the acid rules, and let's practice together. Let's do some together on page 13. My polyatomic ion chart and periodic table are close by. Let's talk about the first one, HCl. I want to name this as an acid. Well, first of all, I notice that it's binary. And binary tells me that originally we would have named this hydrogen chloride. I'm going to write much larger just so I can fit it into the note pack. You certainly can fit all of this in margin notes, but I want to write large enough so you can see. So HCl. I'm reminding us that it's a binary acid. I would have named this hydrogen chloride. I would have named it, but now let's name it correctly as an acid. If the original ending were IDE, we go hydro, root word ic. This correctly is called hydrochloric acid. HCl, hydrochloric acid. Number 2, HClO3. I know it's an acid because it starts with an H. ClO3 is the polyatomic ion. Let's find its name. We know H is a +1. ClO3 must be a -1. So I'm going to look through the first column. ClO3, -1, is called chlorate. ClO3, -1, chlorate. We would have named this, prior to this new lesson, we would have named this hydrogen chlorate. 8. But now say it as an acid. The acid rule, if it ends with 8, turn it to ic. This simply becomes chloric acid. Notice how I am not saying hydro. It's simply chloric acid. Notice the difference here. When I hear hydro in the name, I know it's binary. If I'm not hearing hydro in the name, I know it's ternary. The absence of saying hydro lets me know a polyatomic ion is involved in the formula. Hydrochloric, HCl, then simply chloric, HClO3. There's one more in this family, HClO2. Acids start with H. How we name acids all goes by the negative ion. ClO2 is a polyatomic ion who is called chlorite. ClO2 -1, chlorite. We would have named this hydrogen chlorite. Now let's say it as an acid. Acids always start with H, but when ite is the original last name, it simply gets changed to OUS, us. Hydrogen chlorite, named as an acid, is called chlorous acid. Chlorous acid, HClO2. Let's continue the trend with HClO. Number 4. HClO Starts with an H, so I know it's an acid. I know it's a ternary acid, so it must contain a polyatomic ion. Let's find the polyatomic ion whose formula is ClO. And here it is. ClO negative 1 is called hypochlorite. Here the ITE ending, hypochlorite. So we would have named this hydrogen chlorite. But now let's name it as an acid. Oops, I'm sorry. I forgot my... Let me correct that, please. Sorry. This is called hypochlorite. Hydrogen hypochlorite. That's all one word, hypochlorite. Please repair that with me. Sorry. Now, hydrogen, H, hypochlorite, ClO. Let's name that as an acid. We do not say hydrogen in this. We simply turn the ite to an us, and this is what it sounds like. Hypochlorous acid. Hypochlorous acid, HClO. That's in bleach. Hypochlorous acid. Let's take a peek at number 5. Number 5 on our paper says HClO4. HClO4. This again is a ternary acid. We've had ternaries for many in a row. Chlorous acid is ternary. It contains a polyatomic ion. HClO was ternary because it had a polyatomic ion, and this also is considered a ternary acid because there's 3 elements in it. One must be a polyatomic ion. So we'll need to find ClO4. It'll be a -1 because it's being balanced by a +1. ClO4 with its -1 charge is called perchlorate. Perchlorate, all one word. So we would have named this as hydrogen perchlorate. 8 turns to ic, and we do not say hydrogen for these ternary acids. We simply turn 8 to ic, and we come up with perchloric acid. Perchloric acid, HClO4. Let's go back and find our next example. Number 6, H2S. Number 7, H2SO3. And number 8, H2SO4. This looks like a family of acids. Number 6, H2S. Number 6, do you recognize that as a binary compound? It is binary. It only is made of 2 different elements. I know that binary compounds originally ended with "ide." We would have named this hydrogen sulfide. Now it's worth mentioning, why do we have a subscript all of a sudden? It's just all about balancing charge. I know H is a +1, sulfide is a -2. So when I crisscrossed a +1 with a -2, you can see why now the hydrogen has a 2 after it for its formula. Does not play a role in naming it, it's just there to balance charges. Now, to name H2S as an acid, it's binary. The original ending was "ide," so we hear hydro, root word, ic. Name this as an acid, hydrosulfuric, put that syllable in there, hydrosulfuric acid. Say it in your head with me, hydrosulfuric acid, H2S. Binary compounds, we do hear the hydro prefix. Notice in number 7, H2SO3. I bet you recognize right with me that this is a ternary acid. Ternary. That means one of these is a polyatomic ion. Let's find SO3. It's called sulfite. Sulfite, SO3 -2. Do you see why now we have 2 H's in our formula? We're just balancing the charge. We would have named this hydrogen sulfite, a ternary acid now. Ite turns to us, and we simply write out sulfurous acid. Notice how that sounds correct. Sulfurous acid. Ternary compounds, originally ending with ite. Ite turns to us, and sulfite turns to sulfurous acid. Let's try number 8. H2SO4. This also is a ternary acid, making me know that it has a polyatomic ion involved. Ternary compounds are built of polyatomic ions. SO4 minus 2, we see that as called sulfate. Sulfate. Thinking about the negative 2 allows me to see why I have a 2 after the hydrogen. It's just there to balance charges. H2SO4 would have been named hydrogen sulfate. Now let's name it as an acid. Hydrogen sulfate. 8 turns to ic, and we simply write sulfuric acid. That's called battery acid, sulfuric acid. Hydrosulfuric, binary. Sulfurous, sulfuric are ternary acids with sulfur as its base element. And one more in this series, it's number 9. I see H, C2H3O2. H, C2H3O2. This hydrogen carries a +1 charge. It is not combined with the H's in our polyatomic ion. C2H3O2 is a group of atoms acting as a unit carrying a charge. We never change their subscripts. It's called acetate. Acetate. We would have named this compound hydrogen acetate. But now let's name it as an acid. Acids start with H. Acids are hydrogen ion releasers. 8 turns to ic, and we get something called acetic acid, commonly called vinegar in everyday life. Acetic acid. Hydrogen acetate is a ternary acid named acetic acid. Good work practicing naming. Let's practice writing out formulas. Going the opposite direction. Turning out words into formulas. Working backwards with my handy dandy chart here, naming acids. Alrighty. So here's what I noticed. Number 1, nitric acid. We have to figure out the original ending on the polyatomic ion. Now here's something to consider. I do not hear hydro. So right away, I know it's a ternary acid. No hydro out front. And I notice the ic. I notice the ic as the last name. If it ends with ic and I'm not hearing hydro, no hydro, just straight ic, the original ending was 8. I need to find nitrate. If the original ending on our polyatomic ion is 8, what we're finding on the polyatomic ion chart is called nitrate. And nitrate is right here in the middle of our first column. NO3, -1, nitrate. So I went to work and found the negative, NO3 -1. What's the element that always starts an acid's formula? You got it. It's hydrogen. HNO3, nitric acid. Our second example says hydronitric acid. Hydroic acid. Work backwards. Hydroic acid. Notice here that it must be binary. Hydro is the first thing I hear, and therefore the original ending must have been "ide." Hydro, root word "ic," comes from an original ending "ide." So that means if the original ending were IDE, we're trying to write a formula for the negative ion nitride. Nitride, see these IDE endings? They're coming from the front side of our periodic table. Nitride, N-3. So the beginning here, we've got set with the negative. Acids always start with hydrogen. If hydrogens are plus ones, and we know that from where it lives, H's are always plus ones. N from nitride is a -3. We simply crisscross and we get a binary acid, hydronitric acid, H3N. Hydro root word "ic" tells me it was binary. Let's try the third one. The third one is simply nitrous acid. Nitrous acid. Hear the name. Part of learning a language is saying the name. Nitrous. I notice the ending is OUS. If the acid ends with us, OUS, that tells me the original ending must have been ITE. If the original ending is ITE, we need to find a polyatomic ion called nitrite. Nitrite, from our polyatomic chart, is NO2 and it carries a -1 charge. There it is, nitrite, NO2, -1. A group of atoms acting as a unit carrying a charge. We know that acids always start with hydrogen ions. So a +1 electrically balances a -1, and there's our formula for nitrous acid, HNO2. Let's keep working. Number 4, hydrocyanic acid. Hydrocyanic acid. What do you hear? Hydro, root word "ic." Hydro, root word "ic," tells me it must have been "ide." The original ending was IDE. So the name of the original ion was cyanide. Cyanide. Now most of the time IDEs are indeed binary acids. But when I start finding the element called cyanide, it doesn't exist over here. That's one of those rule breakers on the polyatomic. Remember hearing cyanide? It's a polyatomic ion that ends in IDE. Its formula is Cn-1. Ending in "ide" makes it follow this rule, hydro root word "ic." So the original ending is indeed "ide." It's just a polyatomic that's doing it, Cn-1. Start it with an H because it's an acid. +1 balances a -1, and we get HCN, hydrocyanic acid. How about number 5? This one is called phosphoric acid. Let's go to work deducing what negative ion that was from. I notice the ending "ic," but I don't see hydro. If the ending was "ic," the original last name must have been ATE. No hydro, just "ic." No hydro "ic" comes from 8. So the original polyatomic here must have been phosphate. Let's find phosphate. "Ic" came from 8, and phosphate is PO4 carrying a -3 charge. A group of atoms acting as a unit carrying a -3. If hydrogen is always, always the first name of an acid, we'll have to crisscross the charges to balance it electrically, bringing a 3 down, H3PO4, phosphoric acid. How about number 6? Hydrobromic acid. Hydrobromic acid. I'm seeing here hydrobromic. Hydro root word ic. I just need more paper. Hang on. Number 6. So notice here, hydrobromic. I've already underlined the important clues to figure this out. Hydro root word ic. What was the original ending? Well, it must have been an IDE. Hydro root word ic. Hydro root word ic must have ended in ide. So we need to find bromide. IDE, bromide. And that comes from right here, bromide, Br -1. If bromide, Br -1, H is a +1, hydrobromic acid, HBr, a binary acid, hydrobromic HBr. Number 7, acetic acid. Commonly called vinegar. Acetic acid. I just see the ic, no hydro in front. So what was the original ending? Well, the original ending of ic must have been 8. Ic comes from 8. We need to find the polyatomic ion called acetate. Acetate. C2H3O2 -1, acetate. C2H3O2, and it carries a -1 charge. So when we place our hydrogen out front, hydrogen acetate becomes acetic acid. Do not combine the H's. We wouldn't recognize it as an acid. It has to start with the H in order to recognize it as the acid formula. H, C2H3O2, acetic acid. Number 8, I noticed, and you probably will do the same as I did, it's the same as number 1. We will not do it twice. Nitric acid was already written as HNO3.